At the dawn of the 1980s, the balance of global power rested not only on nuclear deterrence, but on the credibility of conventional force projection. Aircraft carriers were the United States Navy's most visible symbols of that power, mobile airfields capable of imposing political and military pressure anywhere on the globe. Yet beneath this image of dominance, a structural weakness was becoming impossible to ignore. The Navy's primary all-weather, deep-strike aircraft, the A-6 Intruder, was reaching the limits of its design life. Conceived in the late 1950s, the Intruder had been optimized for a very different threat environment. It was large, relatively slow, and increasingly vulnerable to the new generation of radar systems, surface-to-air missiles, and integrated air defense networks spreading across the Soviet bloc. At the same time, strategic thinking inside the Pentagon was undergoing a fundamental transformation. The lessons of Vietnam, combined with the accelerating pace of electronics, computing, and materials science, were reshaping how wars were expected to be fought. Precision was becoming as important as payload. Survivability was no longer defined solely by speed or armor, but by invisibility. If an aircraft could not be seen, it could not be targeted. And if it could not be targeted, it could penetrate defended airspace with unprecedented freedom. This philosophy had already begun to take form in the U.S. Air Force's secretive stealth programs. The F-117, though still classified, was proving that radical shaping and radar-absorbent materials could dramatically reduce radar cross-section. Navy planners watched these developments closely, aware that carrier aviation faced an even harsher reality. Unlike land-based aircraft, carrier planes had no nearby safe haven. Every mission began and ended on a moving deck, often hundreds of miles from friendly territory. Any future naval strike aircraft would need to fly farther, strike harder, and survive longer than anything that had come before. Out of this necessity emerged a vision that bordered on audacity. The Navy would not simply replace the A-6 with an incremental upgrade. Instead, it would leap forward an entire generation. The result would be a carrier-based stealth bomber, capable of penetrating the densest air defenses, delivering precision weapons deep inland, and returning to the carrier undetected. This concept would become known as the Advanced Tactical Aircraft Program, or ATA. Its ultimate expression would be the A-12 Avenger II. The engineering ambition behind this aircraft was immense. From the outset, the A-12 was conceived as something fundamentally different from traditional naval aviation designs. It would abandon the familiar tube-and-wing configuration in favor of a flying wing shape, optimized to scatter radar energy away from hostile sensors. Every edge, every surface angle, and every panel seam would be carefully aligned to minimize radar returns. Weapons would be carried internally, eliminating the radar signature of external pylons. Even the engine intakes and exhaust would be buried deep within the airframe to shield the turbine blades and reduce infrared emissions. This was not simply an aircraft, it was a systems revolution. The A-12 would integrate stealth shaping, advanced composites, digital flight controls, and sensor fusion at a scale never before attempted on a carrier-based platform. The Navy selected a partnership between McDonnell Douglas and General Dynamics to bring this vision to life, combining decades of naval aviation experience with cutting-edge aerospace innovation. On paper, the aircraft promised to redefine what a carrier air wing could achieve. But as the program moved from concept to reality, the scale of the challenge became painfully clear. Designing a stealth aircraft was difficult enough on land. Doing so for an aircraft that had to withstand the brutal stresses of carrier operations, catapult launches, arrested landings, salt corrosion, and constant maintenance, pushed engineering into uncharted territory. The flying wing design, while ideal for stealth, created serious stability and control challenges, particularly at low speeds during carrier approaches. To compensate, the A-12 would rely heavily on advanced fly-by-wire systems and complex flight control software, technologies that were still maturing. Weight quickly became the program's most persistent enemy. Every stealth treatment, every layer of radar-absorbent material added mass. Carrier requirements demanded reinforced landing gear and a robust structure, further increasing weight. As the aircraft grew heavier, performance margins shrank. Engineers found themselves locked in a constant struggle, shaving ounces wherever possible. redesigning components, and rethinking materials in an effort to meet the Navy's demanding specifications. The financial risk was equally unprecedented. The A-12 was being developed at the tail end of the Cold War, a period marked by both enormous defense budgets and increasing political scrutiny. Costs escalated as technical challenges mounted. Schedules slipped. Each delay rippled outward, affecting carrier air wing planning, industrial supply chains, and long-term strategic assumptions. The aircraft that was supposed to symbolize technological supremacy was becoming a lightning rod for controversy. Yet even as the program faltered, its technological breakthroughs continued to accumulate. Engineers were pioneering large-scale composite structures, refining stealth manufacturing techniques, and developing avionics architectures that would influence aerospace design for decades. The A-12 never reached the flight line, but its impact was already being felt far beyond the hangars where it took shape. When the program was ultimately canceled in 1991, it marked one of the most dramatic and controversial decisions in U.S. defense procurement history. Billions of dollars had been spent, and no operational aircraft had been delivered. To some, the A-12 became a symbol of overreach, a cautionary tale about ambition unchecked by practicality. But that interpretation tells only part of the story. In reality, the A-12 Avenger II was a crucible. It forced the aerospace industry to confront the full complexity of integrating stealth with carrier operations. It accelerated advances in materials science, digital design, and systems integration. Lessons learned from its failures informed future programs, shaping more realistic requirements and more disciplined development processes. The DNA of the A-12 can be traced through later aircraft, from stealth fighters to unmanned systems, each benefiting from the hard-won knowledge forged during the Avenger's troubled gestation. Its legacy is not one of flight hours or combat missions, but of influence. The A-12 demonstrated that naval aviation could aspire to the same level of technological sophistication as its land-based counterparts. It proved that stealth was not merely an Air Force novelty, but a fundamental shift in how air power would be projected from the sea. And it reminded engineers, policymakers, and strategists alike that progress in aviation is rarely linear. It advances through bold experiments, costly mistakes, and relentless refinement. The story of the A-12 Avenger II is therefore not a story of failure, but of ambition. It is a testament to a moment when engineers were asked to redefine the limits of what was possible, and they responded by pushing technology into new territory, regardless of the risks. In the long arc of aviation history, such moments are essential. They lay the groundwork for future triumphs, even when they never achieve glory themselves. The history of aviation is written with steel, ingenuity, and the will to challenge limits. The cancellation of the A-12 did not erase the strategic questions that had given birth to it. If anything, those questions grew more urgent. The end of the Cold War did not bring an end to advanced air defenses, nor did it diminish the importance of carrier-based power projection. Instead, it revealed a new reality. Technological superiority would no longer be guaranteed by budget size alone. It would depend on adaptability, integration, and the ability to translate experimental breakthroughs into operationally viable systems. In the years that followed, the aerospace community dissected the A-12 program with forensic intensity. Every design decision, every missed milestone, every cost overrun became a data point. Engineers analyzed how stealth requirements had cascaded through the airframe, how small compromises multiplied into major performance penalties, and how early optimism had underestimated the complexity of marrying low observability with naval durability. These lessons were not abstract. They directly informed the next generation of programs, reshaping how requirements were written and how risk was managed. One of the most enduring contributions of the A-12 was its role in normalizing stealth as a design baseline rather than an exotic add-on. Before the Avenger II, stealth was treated as a specialized capability, reserved for niche platforms operating under highly controlled conditions. The A-12 attempted to make stealth routine, robust enough to survive the unforgiving environment of a carrier deck. Even though it never flew, it forced engineers to confront the realities of maintaining low observable coatings under salt spray, mechanical stress, and constant handling. This experience would later prove invaluable as stealth aircraft entered broader service across multiple branches. The program also accelerated advances in digital design and simulation. Faced with a configuration that defied conventional aerodynamic intuition, engineers increasingly relied on computational models to predict performance, radar behavior, and structural loads. These tools were primitive by today's standards, but they represented a decisive shift away from purely empirical methods. The A-12 helped push aerospace engineering toward a future where virtual testing would become as critical as wind tunnels and prototypes. Economically, the ripple effects were profound. The cancellation sent shockwaves through the defense industrial base, prompting lawsuits, political fallout, and a reevaluation of how government and contractors shared risk. It exposed the vulnerability of relying on ambitious, all-or-nothing development strategies. In response, future programs adopted more incremental approaches, emphasizing technology maturation before full-scale commitment. This shift would shape procurement philosophy well into the 21st century. Culturally, the A-12 occupied a strange space. It never achieved the iconic status of aircraft that flew and fought, yet it became a legend within engineering circles. It was spoken of in the same breath as other ambitious projects that pushed too far, too fast. But among those who worked on it, the Avenger II was remembered less as a failure and more as a necessary step. Many of its engineers would later contribute to programs that succeeded precisely because they avoided repeating the same mistakes. The influence of the A-12 can be seen most clearly in later stealth aircraft designed with a more balanced understanding of trade-offs. Weight growth, maintainability, and life cycle costs became central considerations from the outset. Carrier compatibility was treated not as a secondary constraint, but as a defining feature. The idea that stealth alone could compensate for all other shortcomings was abandoned in favor of a more holistic view of survivability. In this sense, the A-12 reshaped expectations. It taught the aerospace community that revolutionary design demands revolutionary discipline. Vision without restraint leads to collapse, but restraint without vision leads to stagnation. Progress lies in navigating the narrow space between those extremes. The Avenger II marked one of the first times the Navy attempted such a leap, and the scars it left behind became guideposts for the future. Today, when analysts look at modern naval aviation, they see aircraft that embody many of the principles the A-12 sought to realize. Internal weapons bays, reduced radar signatures, advanced avionics, and integrated sensors are no longer radical ideas. They are standard requirements. Unmanned systems, in particular, reflect a lineage that can be traced back to the A-12's flying wing philosophy, leveraging stealth and endurance without exposing pilots to extreme risk. The story of the A-12 Avenger II ultimately reveals a deeper truth about technological progress. Not every innovation succeeds on its own terms. Some exist primarily to illuminate the path forward, showing where the limits lie and how they might eventually be overcome. The Avenger II was such an innovation. It asked questions that could not yet be answered, and in doing so, it prepared the ground for answers that would come later. In the grand narrative of aviation, the A-12 occupies a paradoxical role. It is remembered for what it failed to become, yet its true significance lies in what it enabled others to achieve. It stands as a reminder that the pursuit of mastery over the air is as much about learning from ambition as it is about celebrating success. Each canceled program, each abandoned prototype, contributes silently to the aircraft that do take flight. The history of aviation advances not in straight lines, but in arcs shaped by risk, imagination, and hard-earned knowledge. The A-12 Avenger II was one such arc, rising sharply with promise, falling under the weight of reality, and leaving behind a legacy that continues to shape the skies. As the 1990s progressed, the technological seeds planted by the Avenger II began to surface in unexpected places. Engineers who had wrestled with its impossible weight targets, its fragile coatings, and its uncompromising geometry carried those experiences forward. What had once been isolated experiments became institutional knowledge. The industry learned how stealth behaved outside pristine laboratories, how it aged, how it cracked, how it failed, and most importantly, how it could be improved. The A-12 had forced these lessons early, at great cost, but they would no longer need to be relearned from scratch. At the strategic level, the Navy quietly absorbed a more sobering realization. Absolute technological leaps were seductive, but naval aviation lived in a world of operational constraints that could not be ignored. Carriers were not test ranges. They were floating cities, operating under political pressure, budgetary scrutiny, and unforgiving physics. Any future aircraft would need to be revolutionary in capability, yet evolutionary in execution. The shadow of the A-12 loomed over every requirement document that followed. This recalibration coincided with a broader transformation in warfare. Precision-guided munitions demonstrated their effectiveness during conflicts in the Middle East, proving that fewer aircraft could achieve greater effects if they were properly equipped and protected. Stealth, once envisioned primarily as a tool for deep penetration, was now understood as a force multiplier across the entire battlespace. It reduced risk, expanded options, and compressed decision timelines for adversaries. These insights aligned perfectly with the ideas the A-12 had embodied, even if it had been too early to realize them fully. The industrial impact was equally significant. The cancellation of such a high-profile program forced defense contractors to rethink how they pursued innovation. Partnerships became more cautious, milestones more rigorously defined, and technology readiness levels more strictly enforced. The era of betting everything on a single, monumental design gave way to a more modular approach, where subsystems could mature independently before being integrated. This shift did not dampen ambition, it refined it. From a design perspective, the A-12's flying wing configuration proved especially influential. While it posed immense challenges for manned, carrier-based aircraft, its aerodynamic efficiency and stealth advantages were undeniable. As computing power increased and autonomous control systems matured, these characteristics found a natural home in unmanned platforms. The logic was compelling. Remove the pilot, and many of the constraints that had plagued the A-12 simply disappeared. Endurance could increase, structural margins could be redistributed, and mission profiles could be expanded without risking human life. This transition marked a subtle but profound evolution in naval thinking. The A-12 had been conceived as the ultimate expression of manned strike aviation. Its legacy, however, helped open the door to a future where manned and unmanned systems would coexist, each optimized for different roles. The Navy did not abandon the ideals of the Avenger II. It translated them into a form better suited to the technological and strategic realities of the new century. Culturally, the A-12 remained a reference point, a cautionary legend whispered in briefing rooms and design reviews. Yet over time, its reputation softened. What once symbolized excess gradually came to represent courage. It became an example of what happens when institutions dare to ask the hardest questions, even if they cannot yet answer them. Younger engineers encountered the Avenger II not as a scandal, but as a case study, rich with insights and warnings that could guide their own work. The broader public rarely noticed these undercurrents. To most observers, the A-12 was a footnote, an aircraft that never flew and therefore never mattered. But within the aerospace world, its influence was unmistakable. The materials it pioneered, the integration challenges it exposed, and the procurement reforms it triggered all shaped the environment in which later successes emerged. In this way, the A-12 contributed quietly, indirectly, but decisively. Over time, its story also reframed how failure itself was understood. In aviation history, success is visible and celebrated, etched into museum halls and airshow performances. Failure is often hidden, its lessons absorbed silently. The Avenger II resisted that erasure. Its scale made it impossible to ignore, forcing a rare moment of collective introspection. It reminded decision-makers that innovation at the edge of possibility carries inherent risk, and that risk must be managed, not denied. This understanding would prove critical as aerospace projects grew ever more complex. Software began to rival hardware in importance. Integration became the dominant challenge. Systems could no longer be designed in isolation. Every component interacted with countless others in unpredictable ways. The A-12 had encountered this reality early, struggling to align stealth, aerodynamics, structure, avionics, and carrier compatibility into a single coherent whole. Later programs benefited from this hard-earned awareness, allocating resources accordingly. As decades passed, the Avenger II's unfinished airframes took on an almost symbolic quality. They were relics of an alternate future, one where the leap had succeeded and carrier decks were populated by sleek, triangular silhouettes. That future never arrived in that form, but its essence did. Modern naval aviation reflects many of the same priorities: survivability through low observability, precision over brute force, and systems integration as the core of combat effectiveness. In the end, the A-12 Avenger II stands as a reminder that progress is rarely clean or comfortable. It emerges from tension between what is desired and what is feasible, between imagination and discipline. The aircraft did not fail because its vision was wrong, but because the world around it was not yet ready to support that vision. Time, however, has a way of catching up. The true measure of the A-12 is therefore not found in sorties flown or targets struck, but in the trajectory it helped set. It nudged naval aviation toward a future defined by stealth, integration, and adaptability. It reshaped how engineers think about risk and how institutions balance ambition with reality. And in doing so, it secured a place in aviation history that is both invisible and enduring. The story continues, carried forward by aircraft that owe their existence to lessons learned in silence. The Avenger II may never have left the ground, but its influence never stopped flying. By the early 21st century, the strategic environment that had inspired the A-12 had fully materialized. Advanced integrated air defense systems were no longer theoretical threats discussed in Cold War briefings. They were operational realities deployed by multiple nations. Long-range radar networks, layered surface-to-air missiles, and increasingly capable fighter aircraft reshaped the calculus of power projection. In this environment, the core ideas behind the Avenger II no longer seemed premature. They seemed inevitable. Naval aviation entered an era defined less by individual platforms and more by ecosystems of capability. Stealth, once viewed as a singular attribute, became one element within a broader architecture that included electronic warfare, networked sensors, data fusion, and standoff weapons. This holistic approach reflected lessons that had been learned painfully during the A-12 program. Survivability was no longer about one breakthrough technology, but about how multiple systems work together under combat conditions. The most visible inheritors of this philosophy were aircraft designed with restraint informed by experience. Designers accepted that perfect stealth was unattainable, but meaningful reductions in observability could dramatically alter enemy decision-making. They recognized that maintainability and cost mattered as much as radar cross-section. In this balanced mindset, the spirit of the A-12 found its most enduring expression. Its failure had clarified what success would need to look like. Unmanned aviation, in particular, became the natural successor to many of the Avenger II's ambitions. Flying wing designs re-emerged, no longer constrained by cockpit visibility, pilot endurance, or ejection safety. Autonomy and remote operations solved problems that had once been insurmountable. Long endurance, internal payloads, and extreme stealth could now coexist without forcing impossible compromises. The A-12 had revealed the potential of this configuration. Later generations finally possessed the tools to realize it. Socioeconomically, the A-12 reshaped how governments justified and communicated large-scale technological risk. The program's collapse had eroded public tolerance for opaque defense spending, accelerating demands for accountability and transparency. This pressure influenced not only aviation projects, but defense policy more broadly. Procurement processes became more structured, oversight more aggressive, and the language of innovation more cautious. Yet within that caution remained an understanding that stagnation carried its own costs. For the aerospace workforce, the Avenger II left an indelible mark. Engineers who had confronted its challenges became mentors, passing on hard lessons to a new generation. Universities incorporated case studies drawn from its history. Design reviews echoed with warnings born from its missteps. In this way, the A-12 lived on as institutional memory, shaping decisions long after its cancellation faded from headlines. Culturally, the aircraft achieved a rare status. It became a symbol not of embarrassment, but of ambition at the edge of possibility. In aviation lore, there are machines that succeed gloriously and machines that fail quietly. The A-12 did neither. It failed loudly, expensively, and publicly, forcing an industry to reckon with its limits. That confrontation ultimately strengthened the field, grounding future dreams in more durable foundations. The influence of the A-12 can also be seen in how designers began to think about carriers themselves. As aircraft grew more complex and valuable, the carrier was no longer just a launch platform, but a node in a larger network. Emphasis shifted toward distributed operations, survivability of the fleet, and flexibility in deployment. Aircraft would no longer be expected to do everything alone. Instead, they would operate as part of a coordinated system, sharing information and responsibility. This systems of systems thinking aligned closely with the integration challenges first exposed by the Avenger II. Over time, the narrative around the A-12 matured. Distance softened judgment. What once appeared as reckless overconfidence began to look like a necessary experiment conducted at the wrong moment in history. Technology had been pushed beyond what the era could sustain, but that push accelerated progress all the same. Aviation history is filled with such inflection points, where the attempt matters as much as the outcome. The Avenger II also reshaped how success itself was defined. Instead of measuring achievement solely by operational deployment, the industry began to value knowledge gained, capability matured, and future pathways unlocked. In this broader definition, the A-12 occupies a meaningful place. It expanded the design space, revealing both its promise and its boundaries. As modern naval aircraft patrol contested regions of the world, they do so with a confidence built on layered defenses and integrated technology. Their designers operate with a humility forged by past overreach and a clarity sharpened by experience. In that sense, the A-12 is present in every quiet decision to simplify a requirement, to phase a capability, or to delay integration until the technology is ready. Its legacy is therefore neither purely technical nor purely financial. It is philosophical. It taught that ambition must be matched with patience, that vision requires discipline, and that the most transformative ideas often arrive before the world is prepared to receive them. The Avenger II was such an idea. In the long sweep of aviation history, some machines change the world by flying. Others change it by failing to fly, forcing humanity to rethink how it reaches for the sky. The A-12 Avenger II belongs firmly in the latter category, its shadow stretching far beyond the hangars where it was assembled, into the doctrines, designs, and decisions that continue to shape the future of flight. In the final accounting, the A-12 Avenger II stands as one of the most revealing and instructive chapters in the history of modern aviation. It is a story that resists simplification precisely because it sits at the intersection of ambition, technology, economics, and human limitation. The aircraft never entered service, never flew a combat mission, and never validated its promise in the sky. Yet its absence from the flight line does not diminish its historical weight. Instead, it amplifies it. The Avenger II became a mirror, reflecting how innovation truly unfolds when vision races ahead of feasibility. The A-12 was born during a period of extraordinary confidence. The late Cold War era fostered a belief that technological dominance could be engineered decisively and rapidly. Advances in computing, materials science, and electronics were accelerating at a pace few had experienced before. Stealth, in particular, appeared to offer a near-magical solution to the most enduring problem of air warfare: survivability. If an aircraft could evade detection, it could strike at will, reshaping strategy at every level. Within that mindset, the A-12 was not an outlier. It was the logical extreme of prevailing assumptions. What made the Avenger II unique was not merely its stealth ambition, but the environment in which it was expected to operate. Carrier aviation imposes constraints that land-based aircraft do not face. Every design choice must account for violent launches, abrupt recoveries, corrosive salt air, limited deck space, and relentless operational tempo. The A-12 attempted to reconcile these realities with a configuration that demanded precision, delicacy, and unprecedented integration. The resulting tension defined the program from its earliest days. As the aircraft grew heavier and more complex, the gap between expectation and reality widened. Each solution generated new problems. Each compromise threatened to unravel the carefully balanced stealth geometry. Engineers found themselves trapped in a cycle where progress in one area produced setbacks in another. This was not a failure of intelligence or effort. It was a collision with complexity itself, a reminder that advanced systems do not behave linearly. Beyond a certain point, added capability no longer produces proportional benefit. It produces instability. The cancellation of the A-12 forced a rare moment of institutional reckoning. For policymakers, it demonstrated that financial investment alone could not guarantee success. For engineers, it exposed the dangers of underestimating integration challenges. For the military, it underscored the need to align operational requirements with technological maturity. These lessons were uncomfortable, but they were transformative. They reshaped how future programs were conceived, evaluated, and managed. One of the most enduring outcomes of the A-12 was a shift in how risk was understood. Previously, risk had often been treated as an obstacle to be minimized or obscured. After the Avenger II, risk became something to be measured, phased, and deliberately confronted. Technologies would need to prove themselves incrementally before being assembled into a complete system. Requirements would need to be prioritized rather than accumulated. Ambition would remain, but it would be tempered by structure. This philosophical shift rippled far beyond naval aviation. It influenced how governments approached large-scale innovation across defense and aerospace. The emphasis moved toward modularity, spiral development, and early prototyping. Programs were designed to fail small rather than collapse catastrophically. In this way, the A-12 indirectly improved the resilience of future efforts, even as it stood as a cautionary tale. Technologically, the Avenger II left behind a legacy that is subtle but pervasive. Composite manufacturing techniques refined during its development became standard practice. Understanding of stealth materials deepened, particularly regarding durability and maintenance. Engineers learned how radar-absorbent coatings interacted with structural stress, environmental exposure, and operational wear. These insights informed later designs, making stealth more practical, more robust, and more sustainable. The A-12 also reshaped how designers thought about integration. It demonstrated that stealth could not be treated as an isolated feature layered onto an existing aircraft concept. It had to be foundational, influencing every decision from the earliest sketches. This understanding would later define successful stealth platforms, where shaping, structure, avionics, and mission systems were conceived as a single, unified whole. Perhaps the most ironic aspect of the A-12's legacy is how clearly its ideas align with contemporary aviation trends. Long-range precision strike, reduced observability, internal payloads, and networked systems are now baseline expectations. The strategic environment has evolved in exactly the direction the Avenger II was designed to address. What once seemed excessive now appears prescient. The difference is that today's solutions are supported by decades of additional technological maturation and institutional learning. Unmanned aviation, in particular, reveals how far the world has moved toward the A-12's original vision. Flying wing designs have re-emerged, freed from the constraints imposed by human pilots. Autonomy and advanced control systems allow aircraft to maintain stability across flight regimes that once challenged even the most sophisticated fly-by-wire architectures. Endurance, stealth, and payload can now coexist without the same trade-offs that doomed the Avenger II. In this future, the A-12 appears less like a failure and more like an early draft of a design that needed time to evolve. Culturally, the Avenger II occupies a unique position. It is rarely celebrated publicly, yet it commands deep respect within the aerospace community. Engineers who encountered its story did not see a caution against ambition itself. They saw a lesson about sequencing, discipline, and humility. The aircraft became a teaching tool, a reminder that even the most brilliant concepts must contend with physics, logistics, and human organization. Over time, the emotional response to the A-12 softened. The anger and embarrassment that followed its cancellation gave way to reflection. Distance allowed a more nuanced understanding to emerge. The program was no longer judged solely by what it failed to deliver, but by what it revealed. In that sense, the Avenger II achieved a form of success that is invisible but profound. The broader lesson of the A-12 is not confined to aviation. It speaks to innovation in any complex field. Breakthroughs rarely arrive fully formed. They emerge through cycles of overreach and correction, enthusiasm and restraint. Each failed attempt refines the next. Progress is cumulative, built on both triumphs and miscalculations. The Avenger II was one such miscalculation, but it was a productive one. When modern aircraft operate at the edge of contested airspace, relying on stealth, precision, and integration, they do so on foundations strengthened by the A-12's experience. When program managers insist on phased development and realistic requirements, they echo lessons learned during its collapse. When engineers balance bold ideas with pragmatic constraints, they reflect wisdom forged in that earlier struggle. The A-12 Avenger II never carved contrails across the sky, but it carved understanding into the discipline of aerospace engineering. It forced a reckoning with complexity at a time when optimism threatened to outrun reality. It reminded humanity that the pursuit of mastery over the air is not a straight ascent, but a turbulent climb marked by stalls, recoveries, and hard-earned insight. In the final analysis, the Avenger II represents a deeper truth about human ambition. The desire to transcend limits is inseparable from the risk of failure. To retreat from that risk is to accept stagnation. To embrace it without discipline is to invite collapse. Progress lies in navigating between those extremes, learning from every attempt, successful or not. The history of aviation is written with steel, ingenuity, and the will to challenge limits. The A-12 Avenger II challenged those limits with extraordinary intensity. Though it never flew, its influence continues to shape the skies, embedded in the aircraft, doctrines, and philosophies that define modern air power. In that enduring influence, the Avenger II achieved what many flying machines never do. It changed the future without ever leaving the ground.